Hello, everyone. Thanks for giving me this opportunity to present my work. My name is Dian, and I come from University of California, Merced. Today, I'm going to present long-endurance set-specific management of biochar applications using unmanned aircraft vehicle and unmanned ground vehicle. The co-authors are Rafal, Derek, and Dr. Chen. So recently, the global CO2 emissions still remain at high, which is 412 ppm. ppm stands for parts per million in 2020, so around 50% higher than industrial revolution began. You may wonder why we care about the carbon emissions, because reducing carbon into atmospherical can reduce the effects of global climate change, improves public health, develop the global economy, and maintains the biodiversity. Soil as the greatest carbon sink is very important for fighting climate change and supplying water. We must minimize soil carbon loss due to the erosion and greenhouse gas emissions into the environment. And carbon sequestration can effectively reduce the carbon emission and enrich soil structures in order to keep soil health. Here is the data of how much carbon we need to do sequestration into the soil. If we increased by 0.4% amount of the carbon into the soil, we could stop the current annual increased CO2 rate into the atmosphere. So, due to the high carbon emissions and carbon management demands, many institutions are trying to develop a system to capture carbon footprints to manage carbon emissions. For example, the World Bank has shown there are almost 70 separate carbon markets that already made policies for charging carbon tax and start some management. However, the big problem or fundamental problem is, how can we effectively manage something that we cannot measure or value properly? Before I talk about our proposed methods, let me introduce some existing solution of sensing soil carbon content. In general, it can be characterized into two aspects. One is remote sensing. It uses space aircraft such as satellite or aircraft such as UAV, and they employ the hyperspectrometer, super expensive and low resolution. The others use UGV to do proximal sensing. First, the UGV itself is costly, and the UGV is restricted to the field road for traveling entire field. So we focused on the UAV and the UGV sensing system together to do the survey missions. So we focused on UAV autonomous landing on UGV while sensing carbon emissions to improve the SSM endurance. In this figure, the UGV would follow the field path, slowly moving on the trail and spray necessary chemicals and biochar if needed. The UAV would fly towards the survey area to collect the carbon emission information. The specific sensing process is that the UAV flies by the top of the survey area, hovering or landing on the crop or field, sampling, and then fly to the next survey area. In the meantime, we consider two cases. First, if the UAV runs out the battery supply, it can fly back to the UGV landing area, preventing a crash and replacing the battery. And second one is the UAV can talk to the UGV to do sensing and actuation procedures by sending GPS coordinates and pre-processed survey information. This pre-processed survey information would be processed by the AI devices on the UAV, such as lice or more carbon emissions informations, so on and so forth. In the end, after finishing the survey mission, we should be able to get a carbon emissions map of the field. Our sensing system mainly consists of UAV and UGV as shown in this figure. We build a UAV from scratch by using lightweight and low-cost Tarot 650 carbon fiber frames. And they equipped with 4 motors, which would give maximum taking off payload with 1.4 kilograms. Using a 9500 milliamps hour battery will support at least 40 minutes. This without any extra payload. In addition, we customized the co-pilot system installation structure by using a 3D printer. The Raspberry Pi is the essential processor for running landing pad marker coordinates tracking, receiving GPS signal from the UGV, and also being able to send UAV GPS location through PixelHawk telemetry to UGV for both communications. The camera we used was the Raspberry Pi camera and downward facing to the ground. The UGV was retrofitted from a toy to tool. The UGV would be programmed by the mission planner for survey path planning and waypoint set up that allows for the alternative strapping to the needed survey area. As we mentioned in previous slides, the total payload of the drone can be up to 1.4 kilograms. The payload of the carbon sensing mission mainly are sensors, biochar, sprayer tank, and backup batteries, and as shown in these figures. The sensors are the microwave and millimeter wave sensors would be equipped on the UAV and UGV. And the UGV can have the heavy payload. The microwave sensor has 18 reprogrammable antennas, and the millimeter wave sensor has 40 antennas, which will be able to capture reflecting signals from the biochar. For more details, please see our previous work in the reference section. The biochar will mainly be equipped on the UAV so that it can spray in situ after analyzing sensing carbon results. The sprayer tank and backup batteries are on the UGV. The sprayer tank can carry anything, such as water, chemicals, and biochar to spray them at a specific location. Here are the sensing mechanisms of why microwave and millimeter wave signals can sensing soil carbon content. The microwave shows the unique features on these different types of the carbon. Next is our approach methods. We designed two fields for demonstrating entire experiments for long endurance SSM functionality of our system. In the first field, the UAV and UGV demonstrate touch and go survey method for SSM of biochar applications. In the second field, we zoomed in on the touch and go method, which involves the UAV landing on the moving UGV with a visual tracking algorithm target and a properly tuned PI controller. The simulation was run on MATLAB 2022B, and the data analytics were also done on the same platform. We mentioned earlier that we employ the microwave and millimeter wave radar sensors respectively, and we set the sampling rate of the microwave at 10 gigahertz and sampling rate for the millimeter is 100 kilohertz. We record the microwave and millimeter wave radar data when the UAV approaches to the desired survey area. The sampling repeat each sensor 20 times at the same location, while technically the UAV would have a small vibration due to wind or GPS signal. The data would be sent to the Raspberry Pi for processing, allowing the UAV to decide whether to spray biochar or send data to the UGV or not. As of the PI controller, we took the waypoint navigation for both the UAV and the UGV of the data distance driven velocity controller is handled using the first equation. And then we take derivative operation to get a velocity of the vehicles. So that after these procedures, we got a position-based PI controller. Once the UAV matches its horizontal speed with the UGV from about well beginning in the frames, the landing sequence happens. There would be 5 RQ markers on the flat surface of the UGV with the same orientation but positioned in an X pattern. 4 large markers at the corners on the flat surface, while a single smaller RQ markers in the center. This was done to allow the Raspberry Pi camera to see the large markers from the far distance during the landing descent stage. As the UAV reduced its altitude closer to the UGV, the larger markers would become omitted from the field of the view of the camera, leaving the smaller RQ marker left as the driving factor of localizing its landing point. During the initial descent stage, the centroid of the marker pattern is calculated in this equation. We evaluate our PI controller's performance based on the landing sequence in these sections. Left figure shows the 3D of UAV landing on the moving UGV precise. When the UAV approaches its last survey waypoint, it starts the landing sequence. The PI controller for the landing sequence was divided into 2 stages. The transition from the survey to the UGV's above ground landing pad, and finally landing on the UGV. During the first stage, showing this red figure, the Y and Z directions converges to 0, while the UAV's X position is catching up with the X position of the UGV. Once the UAV position is caught up with the UGV, the next stage is engaged of the landing sequence. So the UAV is then matched to the horizontal velocity of the UGV while reducing vertical velocity to land on the UGV. The time step size dt we set up 0.1 second, and the UGV moved at 0.5 meters per second. The maximum UAV speed is 1.5 meters per second for the survey missions. And the UAV's velocity is constrained to 0.6 meters per second during the landing sequence. The overall controller performs well and is cost-effective, making it suitable for use in the UAV's edge devices. As of tracking moving target analysis, we used the OpenCV for Raspberry Pi with the Pi camera. A board outfitted with 5 RQ markers was used to test accuracy of the vision system capabilities in determining the distance and position of the markers. The frames captured will determine the accuracy of the marker measurement are shown in these figures. For the far distance in the red figures, the measured distance the vision system calculated the markers to be was 1.81 meters, while the true distance between the markers and the camera was 1.78 meters. The centroid of the group of markers on the board was slightly shifted from the center of the middle marker. While for the closed distance, which is in the left figures, the measured distance of the vision system calculated the markers to be was 0.78 meters, while the true distance between the markers and the camera was 0.77 meters. So they are pretty accurate and close to each other's. Here is the video demonstration for the entire survey mission through the 3 dimensions. So this is the first stage of touch and go survey missions. And so the blue one is June and the black one is the UGV. And so the UAV is moving on the second survey stage. And we zoomed in the landing procedures in this area, and it's close to the UGV. So it starts to target on the UGV. UAV is making a good slightly turn to approach to the UGV. So it's almost to catch up with the UGV's current location, and the camera system is start triggering. So it's still calculating the arrow, and right now it's going to land. So landed on the UGV. So here's the conclusions and future work. We proposed a long endurance set-specific management system and sensing and actuation system for biochar applications. Our design has several advantages. We have proposed a non-intrusive carbon emission sensing and suppression methods, which both combining on the UAV and the UGVs. Second, we have the long endurance implementation by UAV landing and taking off from the moving UGV. Last one would be the low cost. It's due to the edge computing or our co-pilot systems. In the future, we're planning to working on our system by writing to the ROS2 and also the gazebo. We would like to apply the XAI, which is explainable artificial intelligence, in power to smart sensing system and also smart biochar applications. These are the selected reference. Thank you. Any questions?